Hey, what's up, everyone? We've got the cephla team here on the call. They're stoked for this weekend. They can't wait to see what you build. For a lot of people, they're like, what the heck is robotic microscopy? So we've got Pranav and Wei here. You both want to just give a quick introduction, a couple lines on yourself, and then we'll jump into what is this and how can people build with it for this weekend?
Sure. Thanks, Mike. So I'm Pranav. I'm a clinical research scientist at cephla, at cephla we build automated microscopes for disease diagnosis and for discovery, scientific discovery. Yeah.
Hey everyone, my name is Wei. I'm currently working on like a lot robotic microscope, which you guys would be interested in. I'm leading a group. I'm also, doing research on this early user of cephla microscope. Um, so I'm looking forward to this, see what you build.
Awesome. Appreciate the intro. Pranav, I know you got a few slides to help introduce both the opportunity and the tech stack. I'll let you take it away.
Yeah. Thanks. So in general, microscopy is a pivotal tool in disease diagnosis, particularly in low and middle income countries where sometimes in health posts, all you have is one microscope detecting multiple diseases. Now, there's uh, a lot of potential for making this automated in many fronts. So we can have automation at the scanning. So this can be a robotic microscope, but also at the disease detection using AI. So this combination makes it really powerful, and we can have automated microscopes that can detect multiple diseases. That's where octopi comes in. That's the vision for octopi, which is an automated microscope that we're building at cephla. So here we have some diseases that can be detected by microscopes, and uh, these affect millions and billions of people. So we're focusing mainly on malaria and other diseases like sickle cell disease, tuberculosis. But then uh, the same platform that we're building can be used for multiple diseases, and yeah, we're constantly looking for clinical collaborators that can expand this. So octopi is again a robotic microscope, which is fully automated, low cost, scalable, and uses a conventional glass slide interface, which is yeah, a standard glass slide, and we're removing the barrier uh, for using it in different field settings, and it's adaptable to the current medical infrastructure. And uh, the general framework of Octopi is we have a modular and configurable hardware. So we can do different modes, so bright field fluorescence, other different modes. And then because it's robotic, we have a very high throughput of a large set of images. And then we can use that to generate an open access data set, improve deep learning models, machine learning models, and then uh, deploy it and then iterate to improve the models. Uh, we're uh, we have clinical partners around the world right now focusing on malaria, sickle cell disease, and other diseases like TB, pap smear, and so on. And we're hoping to we envision Octopi to have be like an app store for diagnostics where the same microscope can be used for multiple diseases, diagnosing multiple diseases. I can talk a little bit more about the data set that we have. So, um,
Yeah, I think before we jump into the data set, I
yeah.
think can you give us an example for what high throughput actually means? Because I think for
Mhm.
people who hear that, they might like have a sense, but it's very different. So maybe just give like some numbers, either as an example for something on the
Yes,
slide, just so we have a benchmark of how much high throughput is.
yes,
Yeah.
for sure. So let me show you this interesting video. So this is uh, a slide, one whole slide that has roughly 10 to 20 million red blood cells, and you can scan the entire slide within a few minutes, and also analyze and process that slide, uh, including yes, real-time segmentation and classification actually. So this is uh, wait, so. I have one video here where we're doing real-time detection of malaria parasites where uh, uh, each field of view, it's scanning almost every second. Each field of view has roughly 7 to 8,000 cells. And if a human were able to do this, it would take, yeah, hours even. Like, so this is scanning a lot, millions of red blood cells within a few minutes, and even doing AI or ML based classification on it. So this is the potential for the high throughput again. And like I said, we're focusing on malaria, but then this can be applicable to a lot of diseases. It's a powerful tool that, yeah, can be applied to.
Super helpful to see the live demo and even the tracing of number of cells. So appreciate
Yeah,
that. And yeah, feel free to introduce the data set and I have a couple questions I'll ask after.
sounds good. Thank you. Uh, So the data set that we have right now is on sickle cell disease. This was data collected in Nepal and in Canada, and we have. Yeah, I'll go over the numbers, but then in general, this is what's called a sickling test, where we have, for instance, normal cells, and then we add a sickling reagent, and then over time that doesn't change. But then if we have uh, sickle cell trait, which is again, it's um, not as severe as sickle cell disease. Sickle cell trait is the asymptomatic form of this inherited disease. It's again, it's asymptomatic, so they don't they don't present with any symptoms, but then they can have children that have sickle cell disease. So it's very important to screen for them as well. So for sickle cell trait, you do see some cells that change their shape to sickled shape, but then it's not as pronounced. But then if we have, for instance, sickle cell disease over, yeah, 2 hours, most of the cells turn into sickle cell. So we have this data set where we have collected over 300,000 images. And this, by the way, is just a small cropped part of the image. It's the same scale as the malaria data set, where each field of view, each image has roughly 3 to 7,000 red blood cells. And we have over 300,000 images collected, and then in an open access database, which you'll have access to. And it's not just these snapshots, but then we also have movies. So you can observe this cell in the middle. It changes its shape from round to sickle. And something like this, yeah, hasn't been observed much, but we have uh, whole fields of view, again, like thousands of cells changing the shape over time. And this dynamics is something that's quite interesting and can also be used for detection, but we haven't done that. So yeah, if any of you are interested in doing that, feel free, because that's the edge of the where we are at scientific research. So I mean, you'll have access to these images where you can play around with data sets like these. And yeah, for instance, this is for sickle cell disease and for sickle cell trait. Uh, I'll give you a quick hint. You can already see that the final shape is a little different for both of them. So you can probably use that um, for detection. And again, I'll let you all explore that, but these are some of the examples of the images that you can play around with.
Awesome. Appreciate the walkthrough, the intro. I think we've got other docs we'll share, so I think we'll keep this light. I think just one last question I have is, tell us a little bit more about what open access means, because I think, especially on the software side, there's huge war right now between closed source, open source. Is it actually open source, or what does that mean? And I think it gets even more complex when you have hardware, clinical data, and models on top of that. So I think for people who are curious around maybe helping with other diseases, this hack, we're focused on sickle cell, that's the data set, but be it malaria, TB, help us understand what does open access mean for you all with the octopi, and yeah, help us understand what that means.
Sure. Yeah, I think from the very beginning, we were quite clear that we wanted an open model. So open source software. So all our software and models are on GitHub, and open access for the data set. Now, for clinical data, it has to be very, it's important to handle it well because we have to make sure that the images cannot be traced back to the participant. So I think before doing that, it's very important to go through the proper ethics protocol to make sure that you can release the data open access. So for example, for something like sickle cell disease, uh, we de-identify these images, so there's no link between the patient and the data set, and there's no way for just by looking at this that you could even tell where the patient is from. So like someone from Canada, so the data that I just showed, it's not clear whether it's from Canada or from Nepal. Like I wouldn't be able to tell. Uh, I think there are considerations, especially when we're looking at clinical samples. It's important to consider things like that. Yeah.
Yeah, that makes sense. And I think last question I have, the docs really explain the technical challenges and the opportunities, just going more in a traditional ML perspective. I'm curious, are there different applications that you all think about? I think the clinical workflow starts to make sense in terms of detection and eventually diagnostics. I think the things that don't make sense yet, or they're just so new, is when you start having different humans in the loop or different multimodality. So like, for example, we just had a Sprint member demo a voice agent to a robotic surgery company, and just voice wasn't even on their roadmap because it wasn't even possible 8 months ago at like a high quality side. So is there anything on like the assistant, the co-pilot, the multimodal model that you think might be interesting? And it can still be like clinician in the loop, but there's also like insurance or payer in the loop. There's patient in the loop. There's so many different stakeholders. Is there anything on the multimodal side that again might just be interesting given where we are in May 2025 with new capabilities?
Yeah, for sure. I think something that we were going around earlier also is having an interactive data set. So right now, all these data sets are uh, static, and you can access them and play around with it. But then if you do have an interactive data set, which not just researchers can access, but even clinicians can just access and probe just using, yeah, voice or even like simple text, like how many, for instance, for the sickle cell disease, like how many sickle cells were there in on average. Like I can do the calculations, but then if a clinician was interested in questions like that, then there's a whole uh, new era of discovery for even the clinicians to be able to access this data set, which is becomes very important because then you have the clinician in the loop really for even exploring and yeah finding new possibilities for data sets like this. So
Yeah, and there's more familiarity with the data set than just traditional calculations or traditional model outputs. Is even for partners in our fall program in Ghana, you'd have these lab diagnostic techs who would spend 6 to 8 hours just cleaning, scrubbing medical data just to visualize it internally and then also externally. When it takes hours, it becomes the last thing anyone wants to do after a 10, 12-hour clinical shift. So to be able to have something where you're starting to get information, query. Yeah, there's a lot of interesting opportunities there. Awesome.
yeah.
Well,
Yeah,
appreciate
I
you both.
think
Yeah, go for it, Wei.
Yeah, so sorry. I just want to also comment. I think Pranav already gave a very good overview on this. Just this kind of data set too, because it's so kind of enormous. And I really like this kind of Google Map view, right? You look at it, it's really like and so it supposes a lot of challenges like how do you even host this kind of data set, right? You need some sort of a Google Map kind of server so you can easily stream the data. And especially when you work with some kind of AI models, you need really kind of streaming service, thinking like like the enormous size. And then also when you think about how can you explore this kind of data set, so this kind of language model tools, for example, is gonna be super useful. We have been studied to explore in my team, trying to how can we do that, and a lot of challenges, for example, because the language model, you cannot just throw in these images in the language model, right? And so you really need some kind of design. How can you generate like a low resolution views, and then how can you employ external tools, for example, to generate segmentation mask quickly, get some kind of statistics, and then you feed into the kind of, model context, and then you can produce kind of meaningful answer in a quick way. I think there's a lot of challenges, super interesting to explore. The other thing, I want to mention is maybe because we are targeting, underdeveloped countries, and it's very important to make the machine learning model very lightweight, energy saving, and fast. This is also something to keep in mind.
Yeah, awesome. Appreciate the extra context, and especially around too, like opportunities from being able to stream and host something like a Google Map server, and being able to figure out the right kind of compression or abstraction that makes it just as meaningful to be able to query or use the data in other applications. Awesome. Well, thank you both. We got the 10-minute intro. Can't wait to see what y'all build, and both will be around to support you in your builds.